Hello, everybody. So I'd like to introduce Alex Conway. We're still sorting out a sound, but I'll just do the intro while that happens. So Alex has 126 slides. Be
Oh,
emotionally prepared for this presentation. He is a data scientist and a hacker with more than 25 years of coding experience. He's built startups including an AI development agency, Number Boost, and most recently AI Supervision. He also did a Y Combinator and raised several $1 million from VCs. And he's now exited that startup and is working on applied AI via numberboost.com. So check that out. I think this is going to be fantastic. Are we ready for action? Is your sound working?
I hope so.
Hey, there we go. All right, please welcome Alex.
All right. Hi, everyone. Thanks for coming. So we're going to be talking about applying AI with Python. I'm Alex, and I'm going to take you down this rabbit hole. If you have any questions, you can find me on social media. And I've been doing this for a long time. I worked as a quant in finance. I was the first data scientist at Superbalist. I started an AI consulting company after winning a bunch of projects and prizes, mainly in computer vision. I started a startup that does AI in factories in Germany. We did YC. And now I'm back to doing AI research and like working on lots of different interesting things, which I'm going to show you in this presentation. But I have 8 notebooks, 150 slides. So let's go. This is going to be fast paced. The code and the slides are on GitHub. You can scan this QR code or type in the text and access said slides and presentation. So, what is artificial intelligence? Well, I figured no better way to find out than to ask AI what AI is. And, it takes one to know one. And apparently, AI refers to the simulation of human intelligence in machines. So, this is like getting a computer or a device to do something that a human would need to be intelligent to do. And that at its core, AI models take input data, apply transformations using learned patterns or algorithms, and then produce a desired output. Which sounds a lot to me like a Python function. You just have an AI model function that takes an input, does some algorithms, whatever that means, and then returns some output. And one of the arguments I'm going to make today is that you can, by and large, just use these functions. You don't really need to invent these functions because open source is awesome. So what does this look like? Well, the input can take one of many forms. Typically, it's one of a table, like structured data, or a table representation of like a graph structure or some kind of text tabular data, image or video, text, or audio. And the algorithms, well, I'm not going to go into like every different algorithm. I'm just going to go through some terminology quickly. Mainly because if you are trying to solve a problem using AI, if you use one or two buzzwords in your ChatGPT question, you say like, hey, give me some Python code that can take an input and produce this kind of output. You can even give it like screenshots of the input and the output or like a zip file. And then you use buzzwords like using XGBoost or using Stable Diffusion, you'll generally get better results in my experience. So supervised learning is where you train a model using training data, like you have labels or a column that you're trying to predict from other columns. Train valid test splits is just when you're training a model, you need to measure its performance outside of the data that it's seen. So you split the data set. Unsupervised learning is where you find patterns within a data set without labels. So this is like clustering data and things like that. Regression is where you predict a number. Classification is where you predict a category or a label. Generative AI is where you create new data or content. And then there's a bunch of different types of algorithms. Regressions are for like predicting numbers. Decision trees are good for predicting numbers, regression and classification. Clustering, you can do things like k-mean, spectral clustering. Neural networks have dominated AI for the last 15 years because pretty much every problem is best solved with a neural network outside of some like niche table problems in my experience. And it's unlocked all these cool things with like images and video and text, etc. But don't panic. No math here. All you need to do is be able to copy paste. It's funny, like I had this conversation with someone here yesterday, and they're talking about writing code, and it occurred to me that I haven't written code in like 6 months. I literally just copy paste code out of ChatGPT into my IDE. And you'll get a sense for what these algorithms and the inside of this function, that you need to do AI, what they look like as we go through these Jupyter notebooks. So yeah, there are examples coming. Brace yourself. And then the output takes the same kind of form as the input. It's just one of a few different kinds of formats. I mean, until we get machines to be able to smell and touch, it's just those three sort of senses. But you may be transforming a table into another table column. Like, for example, if you're trying to predict the quality of a wine based on some input data, which we'll look at in a second. Or you might be taking a photo of a parking garage or something like that and wanting to count the cars in the parking garage. Or you might want to be counting people or cars from a CCTV video. You might want to be turning images or video into text. This is called image captioning or video captioning. So this is, you have an image and you have a function, and the function converts the image into an output that says what the image is. You might be wanting to do image to image or video to video. For example, the Google Translate app's really cool. It like writes the translation in the font and the colors, and like there's a diffusion model that's making that look realistic. There's also crazy stuff going on in video to video. Doesn't sound like it's going to play through the loudspeakers, but that might actually be a good thing. I'll just go back to that. We'll go without sound. The video is just showing.
Be cold, or whether the weather be hot.
We'll be together whatever the weather, whether we like it or not.
Whether the weather be cold, or whether the weather be hot.
We'll be together whatever the weather, whether we like it or not.
Whether the weather.
Crazy. Yeah, so don't believe everything you see on the internet. As always, same rule. Or, we might want to go from audio to text. This is image captioning, like on YouTube, or transcribing. Audio to table. You might have an audio file, and you might want a function that can transform that audio file into like some structured data about the call that you need. Like what are the emotions? Is the call center agent getting angry? Which speaker is it? Is it like an argumentative flow, or is it a smooth conversational flow? Yeah, like audio to text and vice versa with Google Translate and similar apps, text to image. There was a talk yesterday on Stable Diffusion. I actually tried some prompts in Stable Diffusion yesterday, and if you ask Stable Diffusion for a photo of a Python programming language conference in Cape Town, you get this, which actually looks kind of reasonable to me, until you zoom in. The guy. So yeah, models hallucinate sometimes. You might also want to do text to text for something like translation or style transfer. One thing I do often is I'll tell ChatGPT, like, take this text and write it in a different style, and you'll just get back the same semantic content, but in a different tone or style. Text to tables, there's a lot of ways you can do cool structured data NLP. Like, you might have some text, and you might want to run it through a function that extracts all the entities in the text, like where are the people, where's the locations, where's the places, which you store as like a tabular data. So why Python for AI? Well, it's somewhat easy to use, and machine learning researchers often are not software engineers. They're like math people or like physicists. So they gravitate towards Python. Massive community, so it's easy to find answers to questions. And also that means that GPT is good at Python because it scrapes all the internet. Extensive libraries and frameworks, and I'll again make this point that you don't need to invent something to use it, and you can just use these great libraries that are really useful and sometimes would save like years of work. And by and large, my hypothesis is that like 80% of the AI tasks that you'd want to do as a software engineer, like check if there's nudity in an image, or extract data from a passport photo, or like whatever the business case is, you can almost certainly find an example in one of these frameworks that you can just adapt, and you don't need to really understand any of it. And yeah, I mean, if I were to try to teach someone how to get good at data science, I would say do your own examples in each framework. So just come up with a couple cool examples, collect data. That might be like setting up a security camera outside your house and like counting the cars that go past, or it might be something else. And also check out Hugging Face. So Hugging Face is like a data and models repository, where you can see all the latest trending models and also models by category. So if you zoom in on that website, they've got sections for models, like the top section's all image and video, then text, then audio, and tabular, which again is the kinds of inputs and outputs that we've been talking about. And you can go to Hugging Face and just click like key point detection, and it'll give you a model that you can use for key point detection. Let's say you're building an app where you're trying to like count reps when someone's weightlifting. You'll need to do pose estimation or key point detection. So now you know like where to start. All right, so let's dive into these 4 different types of input outputs to try to give you a sense for some of the algorithms and things that are possible. So table data. We're going to look at this data set on wine quality, and it's got about 5,000 rows and 11 columns. It's some real data from Portuguese wines. And we're going to fit a regression model to predict wine quality. So we're going to take those 5,000 wines, we're going to split it up and use like 3,500 to train a model, and the remaining 1,000 to like evaluate how good the model is. We know the answers, so we can calculate an accuracy. And in some sense, what this is like you could take a new wine and input those 11 columns, and then the model will tell you what the quality is based on those inputs. So we'll look at that in a second. And if you plot some of the data, you can see, I mean, here the green points are white wine and the red points are red wine, but you can see like quite clear distributional differences in some of the covariate pairs of features in the data set. So let's look at this notebook quickly. So we got some imports, then we load some data. These are just the CSVs. Those are some of the columns. We visualize some of the data. I mean, in terms of columns, we've got fixed acidity, volatile acidity, citric acid, sugar levels, chlorides, sulfur dioxides, densities, pH, sulfates, alcohol level, and then there's quality variable and a color variable. Color is 0, 1 for white wine, red wine. Here we just plot some of this data. Again, just you can visually see that there are patterns that distinguish red from white wine. Look at some of this data. You can look at this later, but then we want to predict wine quality. So all we do here is we extract the column we're trying to predict. So that's super easy. It's just like take that column out of the data set. X is usually the features and Y is the target that you're trying to predict. Then we split them into like 30%, 100%, and then split out the test set so that we have around 70% training, 20 validation, 10% test. And then we also scale the variable columns because they're on different scales. And that's about it. Then we get this X-train data frame, and we can quickly use a regression model, a multiple linear regression model. And if we predict wine quality, we get a mean squared error of around 0.55, which means that when the model predicts the quality of a wine, it's usually within 0.5 points of the right answer in the quality model, which is pretty good. But if we use a better model, like a more nonlinear model, something like XGBoost, which is always my go-to model for table data, we get a mean squared error of like 0.39. So the XGBoost MSC is like 40% lower. So even though we had a good model initially, using a better architecture gave us a 40% reduction in error on a relative basis. Okay, and then if we wanted to do something like classification, we do much the same thing, except this time we're going to keep the color column as our target variable that we're predicting. We're going to split the data, scale it again. Here we'll use logistic regression, which is a weird name because regression is usually predicting numbers, and this is predicting a category. But it's the first thing you learn in university in machine learning. And it gets like 99.6% test set accuracy, 98.5% validation set accuracy. It's like very accurate at predicting whether a wine is red or white. And if you plot a confusion matrix, you can see the kinds of mistakes it makes. You also notice there's some data imbalance, like the one class has lots more examples than the other one, so that might be something you want to address. But all I would do is I would give ChatGPT like all this code, and then I'll be like, what can I do to improve my model? It seems like there might be like class imbalance. And just giving that one like little hint to GPT will give you a good solution out the box. And then instead, if we predict with the XGBoost model, you'll see fewer errors. And here the XGBoost model is 2.3 times smaller error than the logistic regression model. So yeah, use XGBoost for tables, basically. And a lot of table models and doing AI on tables comes down to feature engineering. So like you might be tempted to export your sales data and then somehow engineer a churn prediction model just based on the data. But calculating features like recency, how many days since the last time the customer made a purchase, frequency, how many purchases have they made, money values, what's the average value of their purchases. And you can do stuff like enrich this with geospatial data. If you know their address, you can say like, what's the average house price in their neighborhood? And all these features will allow you to do the prediction better. Even how you define the target, like churned, that could mean that they haven't made a purchase in 30 days. It could mean something else. So feature engineering is often where this lives and dies. And again, you can go to Hugging Face, and there's examples for time series forecasting as well. It's a big area of table data, and all these like state-of-the-art algorithms that you can try for your table data problems. And if you wanted to use one of those time series forecasting models, you literally just click one button in Hugging Face, copy the code at the top, and then plug in your data. Image and video data. Image and video data is very close to my heart because I love doing like image and video problems. And computer vision has had a breakthrough really in the last like 10, 12 years. You'll see here that on this challenge to classify the content of images called ImageNet, the best models were getting like 26% error in 2011. And then suddenly that error drops dramatically in 2012 when the first deep neural network architecture was used for this image classification. And since then, it's just gotten better and better. And human error for this problem is about 5%. So we're much better than human level accuracy with these computer vision models. And these are from like 2017. And the ImageNet data set is one of many data sets you can use to train these models. Typically, they're trained with a convolutional architecture. So the image goes in, there's some convolutional layers, some pooling layers, and then it produces one of 1,000 predictions for what the category of the image is. And you can modify this architecture in various ways and use it, and we'll look at it in a second. This is another architecture. It's a much more deep architecture. There's just more levels, and it's also got these skip connections. That's ResNet. So let's jump back to Jupyter Notebook quick. So here we've got some imports, and we're going to classify using a pre-trained model, which you can do in this is like 6, 7 lines of code when you take out the comments. Seems I broke the indentation. But anyway, so you use this pre-trained classifier on an image, and it'll give you predictions. There it's saying 96% sure it's jeans, 1% sure it's a cardigan, and cowboy hat. This one's predicted as a bulletproof vest with 12% probability. And so that's a bit of a problem. The problem is that we don't want to predict. Really, you can do this in like 6 lines of code using a pre-trained classifier. The problem is that we don't want to predict one of 1,000 categories from ImageNet. We'd want to predict a category that makes sense for us. So here, for example, I have 8 categories. I scraped this data from one of the e-commerce websites. It's a couple thousand images across the 8 categories. And so we can't use a pre-trained model because a pre-trained model doesn't know what like shorts are. Just hasn't ever seen shorts before. And we'll get much better results if we train this for our task. So we'll train our own model, which used to be so hard. It used to be really hard to train a convolutional model. It's so easy now. So here we're loading the data. The data is just each folder has those 8 folders with the categories. Then the images get resized and like some pre-processing stuff. Based on the model, it has some associated pre-processing that's required. If we look at this data, you'll see it's, clothing photos from an online store in different categories. Then to train the model, we literally just load this base model, except we have include top equals false, which means that last layer that mapped to 1,000 classes, we're going to now map it to 8 and sort of like fine tune it that it gets good on our data set. And then you call model.fit, and a few minutes later you have a model that's 99.6% accurate at predicting the category of a clothing photo. If you visualize some of these predictions, especially if you look at the ones that it got wrong, like here, these incorrect predictions, it's like it predicted a jacket, but it's actually knitwear, but that looks like a jacket to me, So I'm not like I think it's a sense check tells me that it's good and it's working. And now what's cool is that once we have a model like that, we can use it to generate embeddings and use these embeddings to do even more valuable things than just classification. So we'll be looking at visual search, which is where you have an input photo and then you find that product on an online store's database, basically. This is Pinterest. Nerd moment while we go down this rabbit hole of embeddings. So an embedding is a function that takes an input and produces a set of numbers that's like a fixed size, so like a 300-dimensional vector. And you can sort of intuitively think of these as like measuring different attributes of the input. Like maybe the first number in the vector is sort of telling you the sleeve length. The second one is sort of telling you how much graphics there is. That's not strictly how it works, but like intuitively, that's the way I look at some of this stuff. And you'd see there, like the image at the bottom, when you calculate its embedding, it has a much higher sleeve length than the t-shirt in some intuitive sense. And we're going to get these embeddings by just using an architecture and then taking one of the intermediate representations and using that as an embedding. It'll give us a 4,906 dimensional number. But you can download pre-trained embeddings for text and images really easily. And they're trained in all these interesting ways. I mean, Word2Vec, for example, is this quite famous example where they trained embeddings using this skipgram architecture where you take windows of 5 words and then you initialize vectors randomly and then you try to predict the surrounding words from the middle word and vice versa. In some sense, like if you have the vectors for these 5 words, you'd want them all to be nearby in the vector space. And that kind of process is how you get these vectors in the first place. And then once you've got them, you can plot them and you can observe all kinds of interesting features like the distance between queen and king is approximately the same distance between man and woman. And that direction is like encoding genderness in the semantic vector space. And so you can use that to make queries. And also note that those vectors are points. The head of the arrow is the points that you can plot and treat these as points. And so if we plot using a 2-dimensional representation our images, you'll see that like similar kinds of products are nearby in this embedding space. And there's all kinds of cool work on embeddings, like Clip is really cool, it's the OpenAI embeddings. They can embed images and text into the same vector space. So if you have a description of a painting and a painting, the points will be nearby in that vector space. And you can do, again, cool things with this. Like you can figure out a vector for going from like the capital of a country to the country. And then if you don't know what the name of a capital is, you can just apply that vector and look up the country for a city and that kind of thing. Or here you can move in a certain direction in this vector space and generate more cartoonish images as opposed to more realistic images. So embeddings are cool. Let's do some quick visual search. So for visual search, again, all we're going to do is get embeddings for each of our images. Just got a quick small function for that. Find similar images is just using cosine similarity to measure the distance in that vector space. And then we've got a function to plot. And so here, if you have this input image, you get these output images, which to me are all visually similar. Like there's only like 100 or so t-shirts, so they're not all going to be like gray with a graphic, but these are all like light colored with a graphic, or two dark colored ones with graphics. Same thing for jeans, like it pulls out just jeans, so it's doing its job in terms of doing semantic visual search. So now let's take a look at objects in images. So if you go to this object detection notebook, it's got some imports and then loading a pre-trained model, and then some code to use this model, which again is really small. If you take away the comments, it's like 5 lines of code or something, and then some code to plot the results. And so here we're running YOLO, which is a popular object detection library. YOLO standing for you only look once. And yeah, you can detect objects and images out the box. This is just a pre-trained model. I literally just downloaded the model and ran it on the photo, and it detected 14 people and 4 cars out the box. Now, I would typically want to train my own model that's like got the same test distribution as the training data, in the sense that you wouldn't want to use a pre-trained model. You want to like train a model for your lighting conditions, your like shop location, your types of people, etc. Then let's look at some segmentation. So segmentation, classification is, here's an image, what is it? Of these 10 things, which one of the 10 is it? Object detection is find all of the things in the image and return bounding boxes and names for those things. And then segmentation is for each pixel in the image, predict what that pixel should be, which sounds a little odd, but I'll show you some results here. So again, you can use this so easily. You just run some imports, you load a pre-trained model. It looks like a lot of code because you got to define the mappings from the classes on the pre-trained model. And then you can just use the model, which again is just like 5-10 lines of code. And if we plot the results, it's doing a similar thing to object detection, except it is classifying pixels instead of returning bounding boxes. And this is really useful for a bunch of things. For example, background replacement, where you can first identify the objects in the image and then replace its background to make that car look like it's in a showroom, for example. And there's all smart stuff you can do with stable diffusion to make the shadows and the gloss look realistic and like make it work. But this is just a toy example showing you segmentation. And segmentation is also often useful to like combine with object detection. If you want to do like an inspection project where you're using computer vision to inspect something, sometimes you want to like segment something out, then do the object detection, especially for noisy backgrounds. So, yeah, object detection. You can use it for like emotion recognition, counting objects on conveyor belts, counting people getting into minibus taxis. This was a fun project. Yeah, like inspecting things. Okay, so we've gone through these notebooks. Multimodal models. Multimodal models are really cool. Multimodal models let you input a photo into an LLM, and then the LLM replies, and you can say like, give me structured data about this floor plan, and you'll see on the right, it tells you how many bedrooms, bathrooms, etc., with the square feet and the square meters. Or you might have photos of products and you want to extract structured data. This would be a really hard computer vision problem before, but with multimodal LLMs, it's really easy. Same thing for like extracting data out of passports or OCRing stuff, like OCRing handwriting, it gets it perfect. And once more, I'll bring your attention to Hugging Face. There's all kinds of really cool models and examples that you can use there. Speech data. So I pulled a little clip of a podcast with Guido talking to Lex about how to learn Python. Then I ran an ffmpeg command to split it and have some audio files that we can transcribe. My audio is not working, so I'm not going to be able to like play, and this is using Whisper. So I'm not going to be able to play this audio for you, I don't think. I can play it a little bit here, I
Do you have
guess.
advice for a programming beginner on how to learn Python the right way?
Yes, that goes on. And then here we can use Whisper to transcribe it, and it gets like perfect transcription really, really fast. Like I got this demo up and running in like 5 minutes. It's really easy. Interesting if you compare the large model versus the small model, the large model took about 17.2 seconds on a 30-second clip. So it's still fast enough to be real time, but not super fast. The small model took 3.4 seconds, and they were identical in their outputs. All right. So speech and motion recognition. I want to quickly take you through this notebook. I didn't write this notebook, and I'm leaving it as like homework to run it and get it, like look at it. But I just want to bring your attention to the fact that it's the same thing as the image classification. So doing audio and motion recognition has the same structure as the image classification. Here they define the emotions, they load some data, they're plotting some samples with different categories. Then they convert the audio, these waveforms, into spectrograms, which are essentially showing you the frequency and intensity at each point in the audio wave. And then they fit a convolutional neural network on top of the spectrograms. And you can see here, there's the model. Here's the training step. They get to 93.4% accuracy. And that gives you a model that can take audio clips and tell you, is the person angry, happy, sad, etc. It's crazy. And again, check out Hugging Face for functions and code and latest models. Yeah, stuff like voice activity detection, speaker identification, really useful. Text data, again, that slide's not supposed to be there. So coming back to embeddings for a quick second. Again, you can view these as points, but those points, text data, it is supposed to be there. I was thinking table data, my bad. Welcome text data. We are supposed to be here. So remember these embeddings that we had, these vectors, these would be 2-dimensional embeddings. Actually, they'll be like 300-dimensional or more. And these are like points, and it could be those points that we had, or it could be like embeddings of entire books or something, or movie scripts. Like in some sense, you'd expect Lord of the Rings to be nearby to Game of Thrones because they're like similar, and you'd expect like Pulp Fiction to be a bit away from Mission Impossible, and maybe like the direction there and the direction there tells you like a certain style of show difference between them, or it could be anything. But recall we had these embeddings for images. We can do the same thing and get embeddings for text. And once we have embeddings for text, we can do some really cool things. So has anyone here heard of RAG, Retrieval Augmented Generation? Couple of hands. All right, so RAG is really cool. Essentially, the way RAG works is you have a set of documents. You chunk them into small pieces of like 200 words each or so. You then construct embeddings for those chunks, and also an embedding for the query. So you have like a chat interface, like ChatGPT, and you are gonna add some documents. Maybe they're about your company. Like maybe, for example, it's a law firm, and you want to be able to ask the law firm's chatbot, like, what is the minimum like sale price above which capital gains starts for commercial property in South Africa, and it should be able to like answer just based on that context, and it should not hallucinate. It shouldn't like make up answers that aren't from context. So we want to be able to like take your query and enrich it by adding context, and then say only reply based on the context, and you get much better results, especially for domain specific stuff. So that's RAG, and we'll get these embeddings. You can imagine these embeddings in a space like we did before, and that might be the query, and those blue ones might be certain chunks that are nearby to the query. So those chunks get pulled out and injected into the prompt. So then it has the context. And so that context gets put into this prompt template, and here they're using Llama as their model. Llama is like ChatGPT. Llama is awesome. It's open source, and you can run it yourself. So like if your boss is saying you can't run ChatGPT, just use Llama 3.2, and then they can't be bitching. And then you return the answer back to the chat interface. So that's RAG. RAG is really cool and useful, so we're going to try and implement some RAG quickly. How am I doing for time? Because we started late, and my stopwatch wasn't 7 minutes. Fuck. Okay, so real quick, I scraped some data. I scraped all the PyCon talks data, and the way I got the code to scrape it is I just wrote a prompt, and I gave it the HTML for the PyCon talks page and the talk page, and I said, give me Selenium, and then it gave me Selenium, so I had all the data. You can look at that notebook, and the data looks like this. These are the documents, so this is scraping the text and structured data out of like a join of the speakers and the talks. And then also have the structured data, which is in a SQLite database that looks like this. So that's all the speakers, I think, with the talks and the bios. And then I also scraped the GitHubs of everyone that had a GitHub. On RAG, we need the documents in order to build a RAG pipeline. So, I mean, we've already scraped these documents. You can just take my word for it that we've got this data. And then in this ETL script, we're just joining topics. These topics I got by exporting the talk titles and abstracts and asking GPT to give me a topic on out of maximum 10 topics. So it was just some data enrichment. And then, yeah, scrape GitHub, et cetera, et cetera. Once we've done that, we create a vector store, which is just loading all of the documents. It was just one text file per talk and one text file per speaker. So those all get loaded into a vector database, and it does the embedding as part of that step. And then you just, again, like 5 lines of code, and you've got RAG running. So if you look at some of these, it's like, what is the main topic of the documents? Main topic is talks at Python, speaker documents and abstracts. Oh, then he talks about AI. Yes, here's some talks about AI. How many talks are there about AI? Ooh, that's wrong. And that's because it can't do like logical calculations, which is something that we're going to address now, looking at AI agents. So remember we had this question, how many talks are there about artificial intelligence? We're going to create an agent with a little bit of a like logical architecture. So here you have a question, we're going to do retrieval augmented generation to get the context. Then we're going to ask a GPT API, do we need to call a SQL database to answer this question? If the answer is yes, then we generate a SQL query, which we sanitize and execute. Then we pipe the results of the SQL query into another prompt that says, answer the question supported by these SQL results. And then we have another LLM that checks if the answer actually answers the question. And if the answer is no, then we rewrite the question and start again. Otherwise, we return the answer. By the way, if anyone wants to build an Excalibur generator, I think that'd be a cool project. And please DM me, because Excalibur is just JSON. So it'd be cool if you could like generate those with AI. Yes, we load the structured data into SQLite. I showed you what the SQLite database looks like. What does the agent look like? So this is not a lot of code because a lot of it is comments and conditional logic, but we just have a while loop where it's like the question has not been answered yet, and then that changes to a yes, otherwise it just loops. Then we write the prompt to figure out if we should run an LLM or SQL. If SQL, it does this. If LLM, it does that. Then in here, we just write the SQL query, execute the SQL query, and write an answer that uses the SQL query. And then right at the end, we check if it answers the question and rewrites the prompt if we have to. So what's remarkable about this is using RAG, we got this question wrong about how many talks are on AI. But using agents, we get it correct. There are talks about AI. There are 4 distinct talks, and it got that by using a SQL query. So I'll quickly just show you 1 or 2 outputs in this agent notebook. Yeah, so how many talks about AI? You can see the SQL query, etc. Which speaker has the oldest GitHub account? Corey Zhu, and that's based on it doing a query that looks like this against the database. What was the most popular topic? Python libraries and tools with a count of 9. Which talk should I go to if I'm interested in data science, etc., etc. Which speakers have committed code to GitHub this week? And it works like remarkably well. So I suggest you try this code out. Like you should be able to just run everything through the notebooks and let me know if you have any issues. I would love to like have some time to demo it now, but I'm worried we're going to run out of time in a second. So I'll start wrapping up. So yeah, agents are awesome. Like the fact that you can inject like a lookup into a SQL database or use tools inside of an agent execution flow and like mediate hallucinations, it's all really powerful. Like this post if you know what the F LAM is. So yeah, a LAM is a large action model. And basically it's a kind of AI where it uses multimodal inputs, like image inputs inside of LLMs that can look at a screenshot and then generate Selenium code that accomplishes an objective. So it's a kind of AI where you give it a context and an objective, and it figures out how to like move the mouse and type in keys. Here it's filling in a job application. And if you look on the right, you can see that it's thinking, it's deciding what steps to go through, then it's filling in those fields all on its own. Let me wrap up quickly. I have a conclusion slide. So yeah, as I said, AI is just, it's like a Python function that takes some input, produces some output using some algorithms. Those algorithms are probably going to come from asking ChatGPT. And if you include some buzzwords like the words I introduced today, I think you'll get better results. You can also pull those models from Hugging Face, Scikit-learn, GitHub, etc. And I'm out of time. Thank you.
Thank you. Yeah, that was really, really cool. I think you planted a lot of seeds. I'm certainly curious about a lot of that, and I have a present for you.
Thank you.
You're welcome.
Sweet.
Yeah.